Good morning, everyone. I'd like to start today's plenary lecture by introducing our speaker, Xavier Snelgrove. Xavier is the co-founder and chief technical officer of Worldscape, a Toronto company building machine learning-powered consumer apps. Their first product was called Minuum, a keyboard with a powerful autocorrect based on statistical language models. But now they're focused on something called Dango, which he'll be talking about, which uses neural networks to interpret natural language and suggest relevant emojis, stickers, and GIFs. Xavier designs and builds the algorithms that powers these products. He is a graduate of the engineering science program here at U of T and a dropout of the computer science master's program. Please join me in welcoming Xavier Snelgrove.
All right, so are we all good on the audio? That's great. Okay, so this will be a little bit of overlap, but just like briefly about me. So yeah, I graduated Eng Sci in 2011, so like 1 TO plus PEY. And then afterwards, I started doing my master's in computer science here at a lab called DGP, which is in the Bain Center, and they focus on computer graphics and human-computer interaction, so sort of in that area. And as part of some of the work that we were doing in this lab, myself and my co-founder ended up starting a company around our first product, which was Minuum, which was mentioned there. So Minuum, we launched that as a crowdfunding campaign. It was one of those crowdfunding campaigns that's like way more successful than you expected. So that was right around when I dropped out because I was like, well, I mean, this company is suddenly turning into something and I haven't graduated. Strictly, I tried to just go on leave forever, but the university didn't let me. So that's what I ended up doing. And then more recently, we launched our second product, Dango, which was, as Jonathan mentioned, all about emoji, stickers, and GIFs. And there, that was really based on our experience from Minuum. One of the things that we saw there was that some of the things that people liked the most in the keyboard were some like predictive emoji features we started to build in there. And we decided to really focus on that and see what we could do. And so briefly, so you have a sense that like this is the kind of thing that you can do as a student at U of T. The path we took towards becoming a company is we started out doing an accelerator called UTest, which is connected to Mars and U of T, which is a program for commercializing research that you do here. And then we were incubated by the Creative Destruction Lab at the Rotman School of Business here at U of T as well. And ultimately, we ended up going down to California to do Y Combinator, which is another accelerator in the Valley. So that was sort of our company history. So today, I'm going to be talking about machine learning and artificial intelligence. These are really, really hot buzzwords right now, in large part because they've started to allow us to solve broad classes of problems which were previously inaccessible. They were previously too complex to be able to solve with conventional programming. So I'm going to talk about those areas in the context a little bit of how we do it in Dango, and then some broader applications in the field. Okay, so briefly, what is Dango? So the idea with Dango is like the way that emoji work in sort of a classic emoji interface is you say something like, you know, let's grab a drink, and then you hit the emoji button, and then there's pages and pages of these little images. There's almost 1,200 emoji now, so you have to like scroll through pages and pages of them, and then eventually, oh, there we go. There's the beers, so I'm going to insert that, and it takes forever and is very painful. With Dango, what we do is we have this little assistant that sits on the screen. It works in any messaging app, and it's able to read the text that you're writing, and then it uses a neural network to say, hey, let's grab a drink. Okay, well, I know what emoji are relevant to that sentence. So instead of you searching through these pages and pages, it's able to bring up maybe the beers and maybe that smirking face. And then you can like quickly stick in, let's grab a drink, smirking beers. So it's a much faster way to do that. And we do it, again, stickers and GIFs as well. Okay, so let's think about how you might try to, if you wanted to build this product, how you might go about trying to implement that. So in the conventional programming approach, you might say, okay, well, let's see, I want to predict emoji, so here's what I'm going to do. If the word pizza is somewhere in the sentence, then let's put a pizza emoji on the end of my list of predictions. Okay, and if the word happy is in the sentence, maybe let's put this happy emoji somewhere in my sentence. So this is pretty close to what, for instance, the iPhone does on their keyboard now. They have some basic emoji prediction, like if you type the word pizza, it might replace it with a pizza emoji if you want. This might be the kind of approach they're taking there. Okay, so that works great. Now I can type the sentence, I want a pizza, and a pizza comes up. Amazing. I type, I'm feeling happy, and the happy emoji comes up. Great, my algorithm is perfect. Unfortunately, what if I say, let's grab a slice? Okay, well, hold on. So I want the pizza emoji, but my rules don't cover that. So maybe I'm going to add a little bit more code here. So I'm going to say, okay, if pizza is in the sentence, Or if slice is in the sentence, then we're going to predict the pizza. And so now when I type, let's grab a slice, the pizza comes up. OK, I've solved that problem. Great. Hold on. Somebody just wrote, I'm not happy. But we're predicting the happy emoji. All right, so that's not quite right. OK, what are we going to do there? Well, one thing we could do is we could add more rules. OK, if happy is in the sentence, but if not is also in the sentence, then we're going to predict the sad face. Otherwise, we're going to predict the happy face. OK, and now it works. I say I'm not happy, and I get the sad face. And again, as you can see, this process could go on, because what if somebody says, I wish I were happy? Again, there, none of those words exactly is about sadness, but the meaning of that sentence kind of taken together is about sadness. Or give me some za. Again, another word for pizza. Maybe I could have a long list of every possible synonym for pizza I could ever think of. Or my cat is happy. There's a happy cat emoji. That would be more appropriate to come up if I say my cat is happy than if I say that I'm happy. What a great day. Again, no word there is happy, but it's a very positive sentiment. So I might want the smiley face. I probably also want the sun and maybe like the palm tree. But again, how do I make sure that the smiley face knows to come up in this context? OK. So that's the conventional programming approach. This is going to become totally intractable. It's going to take forever. I could try to write out every single rule that I could ever think of and try to basically articulate the entire meaning of every word and every possible sentence in the English language. That's going to take a really long time. / probably be impossible. So this is really, these sorts of problems for which, for particular examples, it's really easy to see maybe what the right answer should be, but it's really hard to figure out how to write down a general rule that solves this problem across the board. So that's where machine learning comes in, and all of a sudden, right now everybody's got piles of cash if they do machine learning. So what is that? The idea with machine learning is instead of telling it the rules explicitly, you just give it lots and lots of examples of what it's supposed to do, and you build a structure that has many, many, many parameters, that in many cases millions and millions of parameters, that you slowly adjust over time to make it better and better at predicting across all of these examples. So this is like that training process for machine learning. So in our particular case, we'll train it on hundreds of millions of examples of real text where people have used emoji. So we pull those from the internet, places like Twitter, Instagram, whatever. You build this huge, huge data set. And it's got all these examples. And you can see all these different ways people use emoji. So high prints and the crown comes up. This person's just kind of sad because they're single. Never mind, I forgot I'm single. So they have this sad face. That's what I like to hear. And they're kind of happy and doing their nails. Highway driving in the morning, they're expressing just a happiness around that. So they're kind of the A-OK hand plus the beautiful sunrise. And this example, which I love, happy bro, it was cool chilling with you in line for Travis. Got to catch another show, turn up one time. Tongue sticking out, prayer hand. So that's something that I really probably wouldn't have written any explicit rules for. But it's important that somehow this starts to know what the general vibe of that sentence is. All right. So you take these hundreds of millions of examples, and then you just crunch away at so you put them into a statistical model that you have, and you just crunch away for days, typically on GPUs these days. So one of the really interesting things about what's happened recently with neural networks is it turns out that a lot of the hardware that we designed to do graphics for video games is very suitable for doing the kinds of math that's important for neural networks. So you get some NVIDIA GPUs, you crunch away for days and days and days. Training one of our models takes about a week of just grinding away on some of these machines. And then magically, what comes out the other end? This trained model that is now a functioning product. So, I mean, it's a bit more complicated than that, but that's the general idea with machine learning. You get lots and lots of training examples. You adjust your generic system to be able to solve your particular problem given those training examples, and then you ship it to your customers. OK, so in our case, what is learned? So this is a visualization we did for a blog post a while back talking about what trying to figure out what was learned in our system. So this is emoji in semantic space. So what is learned in our particular system is it finds a way of taking the phrase that you're writing and placing it as a vector, as a point in a high-dimensional space that represents the semantic content of that word, what it is that it means. And then it also has placed all of the emoji into that same high-dimensional semantic space, meaning space. And then all you do is you say, OK, well, the sentence is here. So maybe you can see kind of all the hearts right at the tip of this little peninsula there. So maybe if I made a very loving sentence, my algorithm is going to place that sentence there in this high-dimensional space and look around it and say, OK, here are all the hearts. And then those hearts will be predicted. And similarly, if I'd said something that was kind of well, this is kind of blurry, but anyway, there's some cats here. So if I was talking about my cat, probably the sentence would end up over here, and the cat emoji would be predicted similarly. And so these kinds of visualizations, I think, are really compelling for starting to build an intuition about the kinds of things that happen in a neural network. What you can imagine that's happening during the training process, just to give you like a very high-level picture of it, is that originally, everything is initialized randomly. So all of these emoji are just randomly scattered in this space, and every sentence just maps randomly into the space as well. And then with each training example, we kind of move the relevant emoji a little bit closer to the training example and the irrelevant emoji a little bit further away. And then gradually, as you show more and more examples, that causes these things to drift around until they reach the positions that kind of represent their semantic meaning. So at a very high level, that's kind of the idea of what our algorithms do. OK, so why is this so hot right now? Why is it that people are using like machine learning in so many different contexts? Well, one way to think about that is kind of, you may have heard the buzzword that was like really popular a few years ago, and people still use it, but big data. It was this thing that everyone was talking about, where every company was accumulating these large data sets just based on user interactions and all these things. Storage was getting cheaper, more people were doing more things online, that was generating all of this data. And so there was a lot of work just being done in like, how do we like manage that data? How do we store it? How do we make it searchable? All of those sorts of questions. But one of the things that has really allowed people to like find value in that data that they've gathered, there's no way that you can read 100 million tweets and learn something interesting from that. Machine learning has really been the set of techniques that have allowed us to find ways of extracting insights or building products out of all of that data that we've been gathering. So this is interest in the term big data over time, and you can see it kind of peaks, and right around where it's starting to peak, that's really when machine learning is starting to take off as a concept. It's been around for a long time, but it's recently that it's really started having these big successes. OK, so again, one of the reasons you've heard about it so much is that it's had a lot of success areas at various points in time. And then in the last few years, a particular family of techniques called deep learning, it's a particular like structure of neural networks, has become very popular. A lot of the early work for that was done here at the University of Toronto. But those techniques have allowed a whole bunch of problems that were previously unsolved to be tackled. So some example success areas in general for machine learning. Recommendation engines are big. So like when Amazon says, oh yeah, you bought this book, you might also want that book. Or when Netflix says, okay, you've rated these movies, now we have a sense of how you might rate other movies, and we can predict movies for you. Those are examples of like a very common machine learning problem. Netflix is actually famous for, they sponsored a few years ago the Netflix Challenge, which was like $1 million prize for the research group that could do the best job predicting how people would rate movies based on how they rated earlier movies. And I think for a long time, U of T, I don't remember if they won the challenge in the end, but they were like the #1 team for a really long time during the challenge. And then, so recommendation engines is big. Machine translation is big as well. So early on, when people started trying to tackle the problem of machine translation, they tried to do it in a similar way to how I showed the emoji translation system earlier. They tried to write out like this word maps to this word and that word maps to that word and have just a set of like rules that would tell you how to translate from one language to another. Any production system now, like Google Translate, actually Google Translate has just shifted to an end-to-end neural networks model, which is very exciting. But even before that, it was still a statistical model. The way that they would train their languages is they would find big parallel texts of the same text written in English and in French, for instance. And then they would have a statistical model that would, similar to what I showed for emoji, that would learn how to do that mapping. Incidentally, again, Canada has been kind of important for that because all of the parliamentary debates that happen in Canada have to be translated in English and French. So there's this public data set of large amounts of political speech data in both English and French. And so that data set is very commonly used in research to try to build statistical machine translation systems. A very hot area right now is self-driving cars. Google was kind of a leader on this several years ago, but now there's a lot of companies in this space. And self-driving cars, I mean, there's a huge number of systems that come in there, but machine learning is a very big part of that for the vision parts of them, especially for trying to understand, given sensor data and image data, where is the road, where is the stop sign, where are pedestrians, those sorts of things. Speech recognition, there's been huge progress in that. So the speech recognition on Android, again, is a deep learning model that was developed in large part here at U of T as well. And then recently you may have heard strategy games are always a fun area to tackle with machine learning because it sort of sets you up in this like competitive mode with a computer, and it kind of, we all get excited when a computer beats us at a game that like maybe we have an artificial intelligence now that's smarter than us. And just recently, AlphaGo beat the top-rated human at Go for the first time. And Go was very famously, for a long time, considered a game that humans were just inherently better at than machines because the number of possible moves at each turn was so vast that there was no way you could just search brute force and look at all the possibilities, which is a little closer to maybe how a chess program would have worked. So for a long time, that was untackled. And AlphaGo now is a mix of techniques, but it uses a lot of these machine learning and neural network ideas in order to be able to evaluate board positions and board scores. Now, my understanding is that you guys are going to be building a reversi game as part of what you do here. The machine learning approach would be to try to show it lots of examples of games that have been played and how they turned out, and have it try to learn from that how to evaluate a board position. Whereas the more classical artificial intelligence approach, pre-machine learning, would be to more try to search the entire space of possible moves and have an evaluation function at each move to try to score how well you're doing and kind of go from there. And yeah, computer vision is the other big area that's hot right now. There's been a lot of big breakthroughs in the last few years around having computers actually understand what is in a scene that they're looking at. So can they tell the difference between an image of a cat and an image of a dog? Up until very recently, they would never have been able to do that. Now, all of a sudden, they can do that very reliably. OK. So it's a very quick overview of why this is like used in so many different fields. And to give you a sense of this, so this is a talk, so that's Jeff Dean from Google. So he's, I think, their director of engineering. Or anyway, he does something important at Google Brain now. And so Google's really kind of gone all in on machine learning and AI. So this is a big part of what they do. They just have a lot of data anyway. And they've released this software package called TensorFlow, which is completely free and open source, and that you can use to start to build neural network models quite easily. And the mandate of TensorFlow has been they want to like use that across the entire organization of Google and have every group be able to use TensorFlow when there's some aspect of what they're doing that is machine learnable. And so this is just a graph from a talk he gave recently showing how many project directories at Google now include trained TensorFlow models. And you can see that like, they're up to like 4,000 now, and it's been increasing exponentially since they started to release this thing internally. So a sense of that is that basically, even though not everything is going to be a completely machine learned system, it's sort of touching every part of what you do in some way. So they're saying here that they use production trained models in search and Gmail and translate maps, Android photos, speech, YouTube. Like there's a little bit of this stuff in everything now. So I think even if we're not going to like, and I don't really think we're going to have a computer intelligence that takes over the world in the next few years, it is going to be a very important part of programming going forward. It's just there's this whole class of things you can only really solve with these techniques. And as you try to solve a real world engineering problem, there'll always be this like machine learned component going forward. OK. So that sounds great. It's super easy. You just show it lots of examples, you plug in the thing, and then it does all your programming for you. It's not actually that easy. And let's talk a little bit about why that is. So I gave the example of us training on hundreds of millions of messages. It's actually hard to find hundreds of millions of messages. In general, finding data that you need to train these things on is pretty challenging. A lot of the recent breakthroughs have been based on the fact that we had more and more data. And a lot of the same approaches that we can use on 100 million messages might not work if you only had 10 million messages. So getting access to data is a big problem. And one of the reasons that's a big problem, I mean, there are many reasons, but one of the big reasons is privacy. So Facebook is able to train, so this is an example. So Facebook has this paper, Deepface, where they wrote at the time, I can't remember what year this is from, but at the time it was the state of the art in face recognition. And they showed there were some benchmark data sets out there of labeled faces that they could show that their system outperformed anyone else's systems on. But when they actually trained it, you can see here they say the proposed face representation is learned from a large collection of photos from Facebook, which they refer to as social face classification data set, which includes 4.4 million labeled faces from 4,000 people each with 800 to 1,200 faces. And they didn't release that data set. So that's like, and they couldn't release that data set. I mean, people would be very upset if their private photos started to be released for like the general research community to the world at large. So by having access to this large data set that nobody else has, they were able to like really beat the state of the art on face recognition, and they could release their trained models and tell people how they did it, but no one else is actually able to do it because they don't have access to the data. So that's a problem. So unless you work at Facebook, that could be a problem. And similarly, Google's recently added this smart reply feature to Google Inbox. And so the idea is that you're writing an email, and it reads the text of the email and says, okay, well, here are some like ideas of what you might want to reply with. So it's hard to see, but this guy's like, hey, do you have my documentation to use for this thing? And the answers are either I don't, sorry, or I will have to look for it, or I can't even read that. Anyway, I'll send it to you. So this it kind of knows the 3 possible answers you might want here, that you do have it, that you don't have it, that you might have it soon, or that you have it right now. And again, in their paper where they talk about this, they say, okay, well, we trained this on 240 million private Gmail messages. So again, Google can't release a data set of everybody's private emails in order for you to be able to train your own smart reply system. So they're able to build this system because they have that data. You're not. And in fact, it's one step harder for them because in this particular case, they set it up so that the engineers could not look at the data. So the people who are building the system have to kind of like build the system and throw it into this black box that they can't look at and have it train it there because they're too worried. Emails are so sensitive that you can't have like a whole bunch of machine learning engineers and interns at Google reading people's emails. Facebook decided it was okay to have them look at the photos, but the text of the email they can't look at. So they've had to somehow train the system while only looking at aggregated statistics about the actual messages that are there. So not only do you not get access to the data, even they didn't get access to the data in that case. So you might say, okay, well, that's a big problem. Well, maybe I can like go gather my own. And you can, and there are lots of people who are doing this. So this is another challenge with data access, is gathering and labeling large sets of data. So for instance, this is the Microsoft COCO, Common Objects in Context data set. This is a very popular data set. It's an open data set. You can download it and use it. And it has all of these images that are annotated with information about them. But in order to do that, they've had to, it says here, with a total of 2.5 million labeled instances in 330,000 images, the creation of our data set drew upon extensive crowd worker involvement via novel user interfaces. So here they use a system called Amazon Mechanical Turk. And Mechanical Turk is a very popular system to use in machine learning. It lets you make small tasks that humans can do, and you pay a small amount for each task. So maybe like if you label an image with whether or not it contains a flower pot, you might get paid a penny. I've actually spent probably like 20 hours just doing Amazon Turk tasks to figure out how that is. So I've labeled a lot of flower pots. It's very boring. I've made $9. But Microsoft did this work and they released it for free, but this would have cost them a huge amount of money just to like set this up. At the scale that they need to label this data, it's a huge project to do that. So in general, this problem of how do you find data and how do you get labeled data? How do you get like the actual right answer? Like when you're trying to tell the machine what it should do, even though it's really easy, I can look at this image and say, great, this is an image with some sheep in it. And I could tell the computer that. I'm not going to do that 2.5 million times. So it's very hard to find the training data to actually train these things. So that's a big challenge. And then another challenge is even if you have the data, there's this tendency to kind of feel like, okay, I have all this data. Now this has told me like objective truth or objective reality. Now I'm going to train my thing, and it's going to be less biased than any human, and it's going to be this perfect representation of the problem I'm trying to solve. And in fact, there's tons of examples of why this isn't the case. So there's been a few of these. So there's been big problems in facial recognition software where it turns out there was a bias in their training set where they might have only had the faces of some white graduate students because there was some graduate students doing the training somewhere, and then it wasn't able to generalize and recognize faces from anywhere else. So that was a big problem, especially in early face recognition. People are very aware of that as a problem now, so they're trying to be better about it, but it's still an ongoing issue. And you guys may have seen, I think last year, Microsoft tried to release this AI-driven chatbot that you could like interact with. And very rapidly, it descended into being this complete troll. And in that case, people were actually intentionally screwing with it. So people were messing with the data that it was trained on in order to make it go bad. But again, like these systems are operating in the wild. You don't have a lot of control about where your data is coming from necessarily. And especially if you have an adversarial opponent who's trying to make your system embarrass you, they may find a way to do that. So it's really hard to deal with the objectivity. And then there's this paper which got a certain amount of attention mostly because everybody was scandalized by it, because it's pretty shocking. They wrote a paper, so this is actually a joint work with some Chinese university, but also McMaster University here in Canada. And this is like really, I think, highly irresponsible work, where they tried to train it on mugshot photos of criminals in China and learn what facial features would be good predictors of whether or not you're likely to be a criminal. So that's super dangerous work to do, and that what's assuming is that A, that there's some unbiased process by which we're deciding who's a criminal, and B, that if you had a system that was going to like predict criminality, that there'd be some way to use that ethically. There's a number of reasons why this is a problem. This is this system, what it thinks like sort of canonical criminals look like on top, and what it thinks canonical good guys look like on the bottom. This is like, this is on the assumption that data is objective, which it's not. So there's a quote I really like about this, not about this work in particular, but in general, that machine learning is like money laundering for bias. It's a clean mathematical apparatus that gives the status quo the aura of logical inevitability. The numbers don't lie. So this is something to be very cautious of. You don't want to believe that just because you've trained your thing on some data that you found there in the world, now it's like pure, or now it doesn't have any problems. Like, what if the world has problems and you're just reflecting those? So this is a big problem we deal with. What if some of the things that people are tweeting about, we don't want our system predicting? What if there's some trolls out there that are talking about things that we don't want to bake into the product that we build? And that's a big problem going forward. Luckily, the field is aware that this is a problem. So there are a lot of people thinking about this. So here's some work quantifying and reducing stereotypes and word embeddings. So this was work in trying to figure out the biases that machine learning systems are learning about, for instance, gender of professions and things like that. So they would notice that systems would tend to predict, one profession is likely to be a woman and one profession is likely to be a man, and trying to quantify that and understand where those biases are coming from. This was a recent work from Google. Actually, I'm not sure if these guys are at Google, but Google's done some work in this space. Equality of opportunity and supervised learning. There, they were looking at the problem of trying to build a machine learning system that decides who should qualify for a loan and who shouldn't qualify for a loan. So tries to predict based on various indicators whether or not you're likely to pay off your loan. And they, in that paper, talk about how it's very hard to even start to describe the problem of fairness in that context. So if you want to, and the problem of if there's two demographics and you want to make sure that it doesn't discriminate against one of them, how do you even define that mathematically? Because the machine learning system in the end is mathematical, so you have to kind of bake into your objective functions in some way the things that you want it to reflect. So they discuss in here a lot of the different trade-offs of different ways you might try to protect against bias in these systems. Okay, so that's a big challenge, the bias in the data. And very related to this, I think, is the black box challenge. So this first, when I was showing the emoji predictor, this first algorithm here, might be a little bit long, a little bit unwieldy, but it's kind of understandable. You can look at it and say, okay, well, when is a pizza going to come out? Okay, well, when the word pizza or the word slice is in the sentence. I get that. You can read it and kind of know what it's going to do. Conversely, once I train a machine learning system, it looks a bit more like this. So there's just a million numbers, and that's kind of what it's learned, and there's just all these numbers in this thing, in this black box. And like now, I feed text in, and emoji predictions come out. But it can be very hard to actually know what's going on there. And there's a lot of work happening. There's techniques you can do to try to get a sense. And there's a lot of research happening right now in trying to be better at extracting from these black box brains that we've trained, just what on earth are you doing? What do you believe about the world and why? Okay, so that makes it seem, okay, earlier it seemed like it was really easy. Now it seems really depressing. It's impossible to do this. Why would anybody ever do machine learning? Well, so it's not actually that bad. You can get started now. There's a lot that you can do. So there are a lot of open data sets. I talked about the data problem. Regardless, a lot of this has been sponsored by the companies working in this space. There seems to be this large interest by a lot of the big players to just get more people doing machine learning research. I think they have this sense that they're limited just by the number of people trying to solve these problems right now. It's such a new form of programming. It's gotten really hot in the last few years, but still there's not enough people that can do it. So they're trying to get people up and running with this stuff. So ImageNet is an example of a data set of millions of photographs that are labeled with the semantic content of what's in them. This is a bird, this is a dog, whatever. A lot of the breakthroughs in image classification have come from that data set. MS Coco I talked about earlier. YouTube 8 million is a data set from Google with clips from YouTube videos. An audio set is one they just released which is annotated audio clips from YouTube videos. So you can get audio of cymbal crashing and car hitting a thing and a cat meowing or whatever. And you might be able to train a system. I'm not sure what people are going to do with this yet, but you might be able to train a system that's able to generate cat meows or figure out if your cat's meowing or something. Wikipedia is a common data set just to get a lot of text. It's open, obviously, and there's just a huge amount of text in a whole lot of different languages on Wikipedia. Google has released n-gram data. So n-grams are common sets of like 3 words or 4 words. So maybe hello there would be a common bigram, or how are you would be a common trigram. And so they've released something with like millions and millions of n-grams from all of the books they've scanned over the years. So they can't release the book data itself, potentially because they don't want to, but also for copyright reasons. They have scanned everybody's books. They can't just release those now. But what they can do is release some aggregated statistics that you can still do some learning on. And so this n-gram data was actually pretty useful for us when we built Minuum, which was our keyboard product. That's how we could start to build statistical models of how English works. So there's lots of open data sets. The algorithms themselves are open. So this is a screenshot here of a site called GitKive. So if you've heard of Archive, Archive is basically where all of machine learning research is being published right now. And it's because the field is moving so quickly that the time it takes to get your thing published in a journal and actually go to a conference is way too slow. If you have to wait 6 months, the whole field has moved on by then. So people publish their preprints to a site called Archive. So people will have written their paper, they're going to be ready to submit it to NIPS or whatever conference. But they'll put the preprint on Archive so other researchers can start engaging with the research right away. So Archive is a great site to just find things, and GitKive is tracking basically papers on Archive that have open implementations available on GitHub. So if there's some paper you're like, oh, that's kind of cool, if you just go to GitKive, you can be like, download the code for this, I don't know, learning large-scale Bayesian networks with the sparse BN package. So if you want to learn some large-scale Bayesian networks, you can just download that code right now and get going. So there's a ton of open source code here. There's open source frameworks are very popular. So TensorFlow is the one that Google is backing now. They launched it just over a year ago, I think. And that's already really taking over. A ton of people are building their stuff on TensorFlow. Torch is a system that was around a little bit longer, and that's had more backing from Facebook. That's for neural networks predominantly. For more classical machine learning, which is a lot of other different statistical techniques, there's scikit-learn, which is a popular package that you can use in Python that's free, and you can get started with these things as well. So the algorithms get open. The hardware is getting cheaper. So I mentioned that you need to train these things on a bunch of GPUs for a very long time. Well, one thing that's nice is so many people are doing machine learning now that a lot of the cloud computing providers have started to have GPU machines, so machines that you can train your things on, but you can rent them by the hour. So instead of needing to buy a several $1,000 machine to do your training, and then you train something and then you're done and it's just sitting there idle, you just pay for the time that you use. And I assume they also have crazy student deals. Most of these things do. Actually, as a startup, what I recommend is you start a startup, and all these guys are fighting for your business. So they're all going to give you free credits for their platforms. So we've just moved from system to system, and we have basically paid nothing for the hardware that we train on just by shifting from provider to provider. So there's a huge amount of hardware that's available. And there's tons of educational resources. So a lot of people are doing this. You guys are at U of T, which is a great place to be to do this. And you can just take courses here. There are also a lot of free courses available. This is a very popular one. On Coursera, Andrew Ng, who was at Stanford's machine learning course, is very popular. He was also early on involved with Google's self-driving car efforts. He's now at Baidu, where he's doing their self-driving, I think, bus efforts. Anyway, that course people like a lot. This course is actually developed here at U of T. This is Jeff Hinton's Neural Networks for Machine Learning courses. If you haven't heard the name Jeff Hinton, if you're in the neural network space, you'll start hearing that name a lot. He's a prof here who's really pushed a lot of these techniques forwards, and he's become very internationally popular. He's also at Google now. Then this is actually a course. So this was my first introduction to machine learning, was a CSC 411 here at UT. I think they still offer it. So that's where I really got started with this stuff. And actually, in terms of other courses to take here, I mean, that's a fourth-year course. In general, I mean, obviously, programming is very important. Linear algebra I've found very important for this stuff. Statistics is very, very important. So all of those things will help you get set up with the foundation for this. Calculus a little bit, although not totally. And this is another book. This is actually written by a guy who used to be from Toronto, although he's left, not the University of Toronto, but the city of Toronto. Neural networks and deep learning, and it's a very from the basics, methodical introduction to the basic ideas of a neural net with interactive diagrams about what you can do there. And actually, I don't have it on the slide here, but there's kind of a cool site which you guys should check out, distill.pub, which is a new journal that launched just a couple days ago for machine learning research, but with an emphasis on clear interactive explanations. So all of the papers that are written for Distill have interactive diagrams that explain very visually kind of what's going on. It's like a very didactic platform. And that's being backed by a bunch of smart people from Google Brain, from OpenAI, from the New York Times, a bunch of these places. Okay, so there's tons of that. And the other good news, to some extent, is that you're in Toronto. So Toronto is actually a really good city for doing this kind of work. A lot of people do leave. There is like a huge draw. The Facebooks and the Googles of the world are like mopping up talent for these things. I think famously, Uber hired the entire CMU machine learning faculty. Just like they just wanted them and just took them all. And so CMU had to like rehire again. And again, here a lot of the people we've had also at the university have been leaving to go to industry. But there's still a lot of energy in the city. So a couple examples here. There's this big Toronto AI Institute that's going to be starting soon. You probably haven't heard a lot about it yet, but you're going to start hearing a lot more. It's going to be connected to U of T and really about building a bridge between research that happens at U of T and industry. A lot of like interns will be coming out of there to do machine learning work in industry. The Royal Bank's been growing a big AI lab in Toronto as well. GM is saying it's going to open this big self-driving car lab in the outskirts of Toronto, and they're going to be hiring like 1,000 engineers for that. There's a Toronto company, Meta, which was doing deep learning for sort of research and science discovery. They were just acquired by the Chan Zuckerberg Initiative, which is Mark Zuckerberg's philanthropic initiative. He's trying to donate 99% of his money. And this was their first acquisition. So and they're about 25 people here in Toronto. There's this company, doesn't say the name here, this company Kindred, which is very well funded and has been hiring all the smartest people in Toronto and Vancouver as well. And they're doing humanoid robotics. So there's a ton of cool stuff happening in the city right now. There's actually really good energy. So it's a good time to be here. All right. So that's sort of the broad picture, kind of a sprint through how we use machine learning, kind of what machine learning is. I wanted to end off with just kind of my personal bias, which I don't know exactly if this stuff is going to be the most important part of machine learning, but I think it's really cool is synthesis. So not just the understanding of images or the understanding of audio, but the generation of new audio, of new images, and that kind of thing, just because honestly, this stuff's really cool to look at. So I just want to show some examples of stuff that I just think is really awesome. So you may have seen this. This is Google's Deep Dream. So this was actually, I talked about how one of the problems with neural nets is that there'll be these black boxes. It's really hard to tell what's going on in them. So this was an initiative at Google partly to try to understand what was happening with the image classification engine they'd already built. So they built a system that was able to tell if something was a cat or a dog or a house or a shoe, but they didn't really know how it was able to tell that. So one thing they did with this work is they tried to say, okay, what are the individual like neurons in this system? What are the individual parts of this system actually learning? And so they had this technique to try to amplify. They would take an image, and they would look at kind of how it stimulated the various parts of the network, and they would try to amplify that stimulation in different ways. So here they kind of amped up a few of the neurons, and what done is made all these like eyeballs kind of appear everywhere. So what this kind of implies is that one of the things that the network is looking for when it's trying to figure out what's in an image is it looks for eyes. And so if you try to amplify that activation within the network, everything that's kind of eye-shaped in the image kind of amplifies. And also all these little legs appear. And people started calling these slug dogs because you would get all of these like weird little slug dog creatures showing up when you amplify these things. Super psychedelic. You can generate these things now. The code for this is on GitHub and super easy to get running with. People have done music videos in this style. So this was really cool. Another cool piece of work recently was style transfer. So this is kind of, if you guys have used, I think Prisma is an app that implements some of these algorithms that became quite popular a few months ago. This is actually also hidden away in Snapchat. It's kind of one of their miscellaneous hidden features. But there's this idea that what if I like take a neural network that's able to understand what's in an image, and it turns out, I won't talk too much about how it works, but basically they show it a reference image, and then they show it something they want it to move that image into the style of. And it uses these same classification networks that like Google had, and they have this trick that allows them to copy the style from one image with the semantic content from another image. So they would take this image of like these houses here, and they say, okay, do it in the style of Starry Night. And then all of a sudden you get all of this like psychedelic Van Gogh stuff going on, or they do it in the style of Scream, and you get that painting style. And again, that's starting to make it into consumer products now. Just in the last just over a year, I think, one of the things that's been taking over a lot has been generative adversarial networks. So this has really moved the state of the art in how we can generate plausible images. So here they have two different networks competing, where one tries to learn. So in this case, it's trying to generate bedrooms. And they have one network that's trying to forge pictures of bedrooms that it's just made up itself. And then they have another network that tries to figure out if it's a real photo of a bedroom or a generated photo of a bedroom. And they train these in opposition to each other. And over time, they get better and better at generating images. And you end up with this. So these are all not real. And actually, if you look up close, you'll see that they actually don't make any sense. They're not real bedroom images. The bed kind of bleeds into the wall, or just there's stuff about them that's a little bit off. But they really do kind of look like photos of bedrooms, which is pretty cool. And then building on this work, people started doing these deep generator networks. So they would take a classifier network, and they would start just having it generate like optimal inputs for each class that it was able to recognize. So they would, maybe the network was able to recognize pictures of lighters, and they have ways of generating now perfect images of lighters for that system, or like a beer glass, or a monarch, or a wallflower. And these are all, and again, if you look up close, you'll see that they're kind of screwed up. So the pool table there is kind of like broken in the middle. They're not real photographs. They're synthesized by the network, but it's it kind of explaining to you what it thinks the canonical beer is, or the canonical pool table. And this is just a kind of cool image of how these actually generate these images. This is it searching, this is gonna be it generating a cheeseburger image. And so it's this like optimization process where it tries to make the most cheeseburger-like image it can. And here it comes. And there's a cheeseburger. So this stuff's really cool. Another one that came out recently is Pix to Pix, that can take a drawing and give it, based on the fact that it's seen lots of pictures of cats, it figures out how to make a cat that has the same edges as your drawing. So here's a creepy monster cat based on that drawing. You can play with this in your browser now, and it'll, like, you go to that website or just like search for it, give it a try. And then this is that same algorithm applied to video. So this is actually totally synthetic video of the, Françoise Hardy, sorry, some sound, but it doesn't really matter that much. This video is completely generated based on the facial position and markers of another video. So I think in this case, it's actually a video of like Kellyanne Conway, or like an American political figure. But he's taken her facial features and positions, and he's mapped on this generator based on this French actress, I think Françoise Hardy from back in the day. So this is totally synthetic, and eventually she gets talking, but. So it's creepy. It's not quite right yet, but it's really cool that we can do this at all, right? This is like totally like cutting edge that this is possible.
Okay. No, excuse me. Oh, no. That reporter.
All right, so that's just the cool part, because I just think that stuff's awesome. So that's it. That's basically a very high-level intro to kind of what machine learning is and like how some people are using it in industry. Yeah.
Yeah, I just wanted to point out while you're thinking of questions that Chan Zuckerberg company that they acquired Meta, and I was just talking to a student who was in APS 105 last year in Jordan Lee, and he has after his second year, he has a summer job working for Meta.
Cool.
So, interesting. I don't know what he's doing.
Yeah, I don't know them super well. Yeah. And I think since the acquisition, they used to be pretty focused on product, and I think they've been freed up to like go more like high-level research. I think they're shifting into education, so they're going to do a lot of work on like AI-driven tools for education. It's kind of cool.
There's two other things I thought of there. One was this lecture was originally meant to be given by a woman named Inmar Givoni, but she works for that company there, the secretive Canadian company, and she got told to go down to San Francisco for
Something secretive.
three months or something. And so Xavier jumped in and substituted for her. And then actually one other thing, one of my master's students, professional master's students, just left Cisco to work for this GM self-driving unit. They're trying to figure out what they're doing in Oshawa. So a lot of activity going on. But anyway, this is one of the most remarkable technologies to come along anymore. So perhaps you have a question.
You can also, if you have questions in the future, you can shoot me an email. I feel like my email is easy to find, or you can ask Professor for it. I'm happy to answer any questions, but yeah.
So isn't like also having a lot of big data bad? Doesn't it take more time to compute the response?
Yeah, so he was wondering if one of the problems with having a lot of data is that it takes a long time to compute the response. There's sort of, not necessarily. So there's two different phases to this. There's the training phase, and that's very slow and expensive, and that's really where all the data comes in. But what you're doing is you're training a much more compact model that sort of distills all that information into the neural net. So for our system, for instance, it takes us a week to train the system, but we can do a prediction in like under 10 milliseconds. And we do that in real time on your device while you're typing. So no, it's not really a problem in that sense. It does still take a while to train, but it's kind of always better in training to have more data because you can just choose to not look at all of it if you wanted to. So there's no real downside to having more at train time. And the big thing, it protects you against a lot of things, but one of the big things that protects you against is what's called overfitting, which is where your system, instead of learning how to generalize your problem in general, just memorizes all the training examples it's seen. You know, if you only had 10 examples, it would just say, in exactly this case, this is the answer. In exactly this case, this is the answer, and it never has to learn to generalize. Once you're showing it like hundreds of millions of things, there's no way for it to fit all the information in, so it has to find general rules. Yeah.
So you said something about like maybe the machine learning stuff that we don't want to learn. Like how often do you filter stuff because that might lead to bias?
Yeah, so there's multiple sides to that. Oh yeah, so again, the question was, I mentioned that there's problems with machine learned stuff we don't want it to learn, and how do we protect against that? So first of all, I think that is still a big open question in the general case. There's a couple different sides to that. So there's a lot of spam in our data, kind of unrelated to like other sorts of biases it would learn. And so we have lots of heuristics that try to filter out as much of the spam as possible early on in the pipeline. It's okay, these systems are pretty robust to like there being some garbage in there. So like there's still some spam in our training data, and that doesn't really matter so much, but that's sort of our frontline things. And then most of the other stuff we've actually had to do, we've basically built a filter, so it ends up learning some things that are problematic, and then we build a filter kind of on top of it where we've sort of taught it kinds of associations that it's not allowed to know, and then it kind of censors itself before it says them. It's kind of not ideal because it means that they're still in there. That's the approach we've taken. That works pretty well onto pretty broad strokes. That's covered like 90% of our cases. There's still occasional issues that pop up, and then we still deal with them. This is true of any kind of data-driven thing, not even like something that's as neural network powered as what we do. So like when Google does its search suggestions, there have been all kinds of issues where like people start to like, you know, why do these people do, and then it like writes out as many like stereotypes as it can. And they've done a pretty good job, and it's pretty manual, right? There's a lot of just like never talk about this, never do that, never, and you just kind of write those out. I think that might get somewhat better, but it's never going to be totally perfect plug and play because there isn't like a clear right answer to any of these questions. These are difficult like human political questions that we're going to like, and like what's acceptable is going to gradually shift over time, and we're going to have to learn to adapt to that. So I think there'll always be a big manual component as well, unavoidably.
How exactly is it possible for companies like to not let the engineers look at the data? Don't they like make the code and like find the code that they show you the data?
Well, there's probably nothing stopping. I don't totally know, so because I don't work at Google, but no, I mean they'll have systems where like you don't have any of the appropriate permissions on your system to be able to read that file. All you're able to do is send code to this machine that is going to do the training, and all it can send back is a set of model coefficients or something. So they'll have some process like that. So yeah, it wouldn't be too hard to build something where you don't get access. The problem is, how do you reveal enough information about the data to let the engineers figure out what's going on and like iterate on their technology while not revealing so much that they can just read every email, and that's always the challenge. There's a big research area kind of broadly outside that about, in general, how can we do blind machine learning, and so there's a field called differential privacy, which is and Apple's been talking about how they want to start doing more of this, where like I can build a system maybe that learns from you without ever sending me your data. So like that would be great for us, for instance. You know, we have all these people using our app and typing on their devices. We don't send the text that they're typing back to our servers because that would be a huge disaster if we did that. But we'd kind of love to learn more from them while they're typing. So as the technology improves, I could imagine getting to a point where we have a little learner running on your device, learning from you, and it sends back insights without sending back actual like raw text or something. I can imagine that's where things will go, but it's still an open research question how to do that.